some possible applications of gauge gravity duality holography to some systems of interest to people in other fields of physics. So, roughly speaking, my first lecture will be mostly introductory material, not directly holography per se. I hope to start talking about how to implement holography in finite temperature quantum field theory in the next lecture. So first, I would like to briefly talk about the type of the physical systems that we would like to understand. And right now we lack strong coupling techniques beyond holography to understand it, and for some other. So these systems are mostly divided into two. I will be talking about mostly two classes of problems. First of all is heavy ion collisions. So I'm sure that Krishna will be telling you much more about that problem. Here I'm just will be drawing a space-time diagram for the heavy ion collisions. Typically, we start the collision by accelerating two heavy nuclei. It could be gold as at RIC or lead at LHC. So at very high energies, ultra-relativistic energies, the initial state of the system in the rest frame in the laboratory frames will look like two pancakes. They are pancakes because we have a Lorentz contraction factor. At relativistic heavy ion collider, the Lorentz factor is about 100. So this side is about the size of the nucleus divided by 100. So it's about 0.1 Fermi, roughly speaking. 0.1 Fermi scale. And then you wait for the moment when these two nuclei collide. So this will be time, and this will be the axis. Let's call that Z. Z is the axis of the beam. So you just follow these two nuclei. And there are several time scales that will be important. First of all, there is something that happened here during the time when these two pancakes overlap. This is the shortest time scale in the problem. It's 0.1 Fermi over C divided by C. Since we are setting the speed of light to be 1, so I would call that that time scale 0.1 Fermi. That is the time scale where things start to happen, where you have two pancakes that pass through each other. This is the time scale when they overlapped. And at LHC, where the energy of the collision is much bigger, clearly this time scale will be much shorter. Now, subsequently, the system will evolve, and there is a simplifying assumption backed by experimental data that people usually make, is that at some point the systems start to behave as if it is boost invariant. Boost invariance means that everything will depend only on tau equals square root of t squared minus z squared. Let me call that the proper time, the time, the boost invariant time. If you boost, if you perform a boost along the z direction, the tau variable will not change, where this eta equal arctangent of z over t will be changing. So the assumption we usually make is that the system is boost invariant, at least in a certain approximation. Then, in terms of this tau, people believe, and there are data that seems to strongly indicates that it is the case, that there is some region in space-time bound between two particular values of this proper time tau, where the system behaves hydrodynamically. That is, it behaves like a fluid the system has completely thermalized at some time, tau. How big is that initial time is still a matter of debate. Most people believe that thermalization happened before time of order 1 Fermi. And then the system evolves. It expands in one dimension. So the temperature will drop. At some point, the system becomes very dilute, and all the particles will form, and the system is no longer a fluid, but just a collection of free particles. And here, this surface is called the freeze-out, the freeze-out time. And let me just give you a very rough estimate of that. This could be about 5 Fermi, or a little bit more. So, there seems to be some range in time where there is an approximate description of the system in terms of a fluid, and the temperature of the fluid T can also be determined experimentally, at least at the surface of the lattice scattering that is measured by looking at the distribution of final particles. Very roughly speaking, the temperature is of the same order of magnitude as lambda QCD at the last stage of the evolution of this plasma. So we are here having a problem of describing a strongly interacting gauge plasma. We know it is strongly interacting because the temperature of the same order of magnitude as lambda QCD. At the same time, it's a dynamical system that evolves in time. So for some questions, for example, one of the questions is the viscosity. The lattice method isn't the ideal method to use. So this is one of the systems that I'm sure you will hear much more about that from Krishna, where there is some hope that the holographic method may tell us something about this system. And the second system I plan to talk about in one of the last 2 lectures, I hope. Second system is the unitarity fermions. I will not attempt to describe the system right now. I will postpone that for the later lecture. It's a non-relativistic system, and I like this system. I'd like to talk here because it's a system that is made in particularly here and studied experimentally here in this building. So let me recall very briefly about the basic facts about holography that we will need. So basically, I'm going to use this opportunity to make some disclaimers about everything that I will be talking about. First of all, we don't know how to do calculation in QCD. So QCD is still outside the range of the applicability of reliable methods using holography. So instead of QCD, I will be mostly talking about N=4 super Young-Mills theory. It's an unphysical system from the point of view of the experimental, from experimental physics. But on the other hand, we will see that they have several nice features that might be also, we can speculate how it will extend to QCD. Within N=4 super Young-Mills theory, I will be talking about the limit of large NC and large stove coupling. So it's a particular field theory in a particular large NC strong coupling limit that I will be talking about. one thing that Joe probably has mentioned it to you is that with in using holography we can describe quark-gluon plasma in quart. In quart because it's n equal 4. So the Young-Mills is dual to a black hole. Okay, and with the metric that I'm going to write down right here. R square, and here's function f, something like 1 over r naught to the 4 over r to the 4. And since the metric is explicit, we can study everything analytically. So probably you have seen this formula for the entropy. The entropy of the black hole is nc squared times t cubed, as computed from the black hole area. What does this formula tell you about is that the plasma is in the deconfined phase because of the nc square factor here. At large NC, there is a very simple criterion to tell you to distinguish the confined phase from the confined phase. The confined phase is the phase where all the thermodynamic potential is proportional to nc square, while the confined phase is where the entropy is of order 1, for example. We don't have the same criterion, simple criterion for finite NC, for example. In QCD, the deconfined phase and the confining phase may be not sharply distinguished from each other, especially when there are fundamental quarks in the theory. And the second thing this formula tells you about, and that is just this T cube, is that the plasma is conformal. It's conformal in particular using thermodynamic relations. One can find that the energy density is 3 times the pressure. There is a numerical factor here that is also interesting. This numerical factor is 3/4 of the free gas, which tells us that the plasma is strongly interacting. There is a correction of order 1 to all the thermodynamic variables. So the fact that it is of order 1, but it is 25% attracts some attention of the QCD people, and I hope Krishna will be talking about that too. Okay, so that is the introduction, and now I'm going to tell you about thermal field theory. So basically, I'm going to give a very lightning course on thermal field theories. So thermal field theory deals with systems with non-zero temperature, and there are 2 major formulations of thermal field theory. One is quite familiar to many people, that is the Matsubara or Euclidean formulation. The other is the Minkowski closed time path formulation. So let us start with the Matsubara formulation of thermal field theory. So in this formulations, we start by noticing that the density matrix of a system at finite temperature is e to minus beta h, where h is the Hamiltonian, beta is the inverse temperature, and all the thermodynamic quantities like free energy, entropy can be obtained by doing different operations on the partition functions of the system. That is a trace of e to minus beta h. So now this one in quantum field theory has interpretation as the trace of evolution operators, but time is now Euclidean. You see there is no I here. The evolution operator usually is e to minus ith. Now we have the time that is imaginary. So we can write this as the path integral if we can follow the usual steps, rewriting the evolution operator as a path integral. And here what we will have is that we have a path integral but over the exponents of the Euclidean action. So integral over d tau dx, right? And then the Lagrangian, say, let me write it down for just a single scalar field theory, m square phi square, where the metric here is supposed to be all plus. It is because we are now in Euclidean time. Another thing you see here is that there is this beta here. That means that the integral over time, the Euclidean time here cannot go from minus infinity to plus infinity, but it is limited from 0 to beta. It is because we have a finite Euclidean time evolution. Another thing you see here is that there is a trace. Trace means that when we follow the usual derivation of the path integral, the trace means that where we integrate over all field configurations that satisfy certain boundary condition. For a scalar field, for bosonic field, the boundary condition is that the scalar field at this end and at this end are the same. It turned out that the same, repeating the same procedure for fermionic field, you will find that there is anti-periodic anti-periodic boundary condition for the fermionic field. So putting the system in this formalism, putting the system in at finite temperature is simply putting the Euclidean quantum field theory in a compactified space where the compact dimension is the imaginary time, and imposing certain boundary conditions for the fields. Let us notice here that the boundary condition explicitly break supersymmetry. So the supersymmetry of the original theory will be hidden, generally speaking, at finite temperature. And you have to search for it in order to find that the original theory is supersymmetric or not. Okay, so this is the formalism that is very useful when we try to understand thermodynamics of a system. And that is the formalism where you can, which lattice QCD uses to evaluate the pressure, for example, of quark-gluon plasma. It is a very nice formalism because, in particular, because the path integral here is very well defined. The sign here is minus. There is no I. The path integral can be evaluated more easily than the path integral in the Minkowski space. Now, suppose we want to compute not just the partition function, but some correlation functions. Following the usual prescription of field theory, what we have to do is to introduce a source coupled to our field. For example, in this case, I would couple a source to the scalar field and then try to differentiate the partition function, which is now the functional of this source over J, and then I will get some correlation functions. And let us try to understand what are these correlation functions in operator language. So we take second derivative of log z with respect to j of x, j of y. And it turned out to be something like this. If we follow, go back to the operator language, it is something like 1 over the partition function, trace of e to minus beta of, so let's actually put here 0, beta minus tau h, phi tau. I will not be writing the spatial index here, minus tau h, phi of 0. Okay. So here I assume that this this point is at time in x equals 0. This is at some Matsubara time that is bigger than 0. So we can translate the what we compute in the path integral language into something that we compute in the operator language. Okay? The question is whether this is something that we would be interested in computing. So, for example, if tau is equal 0, what we obtain from here are the static equal time, thermal average. Say of phi of x and phi of 0. So this factor becomes just the weight factor in the thermal ensemble, and we are computing here the thermal average of the product of two operators, and that is interesting if we are trying to determine, for example, the correlation length in the system. How does this correlation function behave as a function of space will tell us about the correlation length. Okay. So one can imagine computing the correlation length of a thermal system using purely Euclidean Green's functions. However, in many cases, what we are interested in is not just the equal time correlation function, but something that looks like this, phi at function of t of x and phi at 0. So since this quantity involves an operator at some real time, we cannot directly infer this correlation function from the Euclidean correlation function that we can compute using the Euclidean path integral. So it is outside, it is most of the time the correlation, the non-equal time correlation function is outside the Euclidean formalism. Just to give you one example where this might be important, for example, if we have a quark-gluon plasma and we are trying to understand, so you draw some picture here, so suppose I have some quark-gluon plasma and I'm trying to determine how much photons it emits in a unit time. A photon basically is a field that is the gauge field that coupled to the to a conserved current in QCD. Once a photon is emitted, it is going through the plasma very easily because the plasma is optically thin. What we are, one can relate this quantity, the rate of photon emission, with a certain Fourier transform. Of the same type of correlation function, but with two electromagnetic currents. Okay? And this one can derive that using different methods. For example, one can use the Einstein's formula to derive this. But at the end, what physically interesting is beyond the scope of this Euclidean formalism. Any question?
So you didn't understand why you say it's beyond the Euclidean formalism?
So this one is E2 minus h ETH, right, plus phi of E2 minus ETH. So the time evolution here is in real time. Okay, you cannot directly infer it from here. There is actually, if you know exactly the two-point function in Euclidean space, there is a analytic continuation procedure that can tell you something about the correlation function in Euclidean in Minkowski space. Since it is analytic continuation, you need to have an exact data. That any small error can potentially lead to a big error in the reconstruction of the correlation function in Minkowski domain. So we would like to have formalism where we start with some path integral, and by doing a similar differentiation with respect to the source, we can recover the correlation function in real time.
So when you do zero temperature perturbation theory, it's an approximation, but you usually end up doing it in Euclidean space.
And then doing a weak rotation.
Is there a reason why you would expect there to be some sort of Stokes phenomenon or something here?
Okay, so the type of thing that you would like to would do there at finite temperature can be illustrated like this. You measure suppose you are a lattice QCD person, and you measure the correlation functions. So I'm going to draw this correlation function not in real space, but in frequency space. You have data at finite point. Because the time direction is compact, you have data at omega equal to pi IT and the multiple of that, and from that you have to analytically continue to find the correlation function here. Okay. So if you have a number, a well-defined set of numbers that you know you know exactly, then in principle you can try to do that. You don't know exactly, so you cannot do that. The thing is that in perturbation, these things are not commuting. The perturbation theory and the taking the an analytic continuation, they don't commute. In particular, the problem is the following. Imagine that you want to compute the correlation functions of, let's take the operator phi squared because I can explain it better. Suppose you want to compute the correlation function of 2 phi squared at low momentum. You draw a Feynman diagram. So in perturbation theory, you know, you imagine that to leading order, you can just evaluate this one Feynman diagram, and then if the lambda phi 4 here is small, that's all that you get. However, if you are looking at the behavior of the correlation function at small frequencies, that means that the time interval between these 2 points is large. Okay? When the real time is large, when you have one particle that propagates, it scatters off many times other particles. You have a finite temperature plasma, so there are multiple scattering that it can happen, which means in terms of the diagrams that you cannot limit yourself to one particular diagram. You have to sum up an infinite number of diagrams. In the phi 4 theory, actually people work out what kind of diagram you have to sum. This diagram looks like this. So the weak coupling limits sometimes don't commute with the yeah, because of the finite temperature. At zero temperature, it's okay. Yeah, in most of the time, you know the analytic structure of the green functions, so you know that the singularities are only here and here, and you can weak rotate. Yeah. So I agree. So we agree. Okay. But there is a need for formalism that would tell us about finite temperature real-time correlation function. So we are going to describe this formalism here. Okay, so imagine that I'm drawing a plane where here it's a complex time plane. T and tau. Tau is my Euclidean time. So previously we know we have been working with the contours that can be imagined as doing this. It's a contour which in time equals 0 and time equal minus I beta. Okay, and the evolution operator becomes the thermal weight factor. And the problem with this formalism that we want to compute the correlation function between fields that lives off of this line in two different temporal events. So the resolution, so the way to write a path integral that allows us to do that kind of thing is to deform the original contour and make it into something that looks like this. So instead of going straight from time equals 0 to imaginary time, we imagine that we are evolving the system at the end along the Euclidean time axis, but we evolve that first in real time and then go back and then evolve that again in imaginary time. So that is minus I sigma, where sigma can be any number that that we like to choose. So basically we are writing e to minus beta h as the product of 4 evolution operators, e to minus ITH, and then e to minus sigma h, e to plus ITH again, e to minus beta minus sigma h. So it's a very simple trick that we are doing here. But what we are going to do next is to formulate the path integral where the action, the integral over the action, is going to be on this closed time path contour. So this formalism is called the closed time path. Path formalism. We're writing the partition function as the integral. Say again, I'm going to assume that the only field I have is the scalar field, exponent of integral over this contour C d tau, and then dx, and then the Lagrangian of phi. Questions so far?
In this case, by tau you mean the complex coordinate tau, right?
By tau I mean just the imaginary part of time.
Yeah, why is that? Because basically.
Yeah, I have to write here t. Is that what you are asking about?
No, I was saying that since you are formulating, I mean you're basically talking about a path which traverses the complex surface. Won't the path integral have especially the Hamiltonian, won't it have some reflection of that fact? I mean, what is
So the Hamilton, what is staying here?
Yeah.
Inside. So it is actually the sum of 4 integral. The first integral is the usual integral dt. So let me say it from t initial to some T final, initial T final of the Minkowski action. And then it has another piece from T final to T final minus I sigma of d tau. Now this is the Euclidean action. Right? And then there is another piece where I go from T final. So basically here I reverse the time, dt, and then there is a fourth piece. So here basically we have two long evolution in time, but this initial and final time can be taken to be plus and minus infinity, minus and plus infinity.
I'm confused. So you start with the Ti equals to 0. That's
Yeah,
the initial time.
but there is no reason for taking it to be. We can take that to be any number, and in particular, I'm going to, for simplicity, I'm going to take that to be minus infinity.
So you just take the real time goes to plus infinity or something.
Yeah, and that one also goes to plus infinity.
And so operator insertion is in the contour, any place.
The source.
2-point function.
The source we are going to insert it as also as a source living on the contour. Okay, so
that could be that maybe on the first contour, maybe that should be in the real time axis.
so this one will be in the real time axis. This one is shifted from the real time axis by
What
some
I'm asking
image.
is just the purpose of this calculating of this partition function is to calculate the correlation functions, right?
Yeah.
So the correlation function in what time? I mean, in general complex time or real time?
So we are going to be interested in real time.
Yeah.
But the purpose of doing that in general, so I will talk about that. Mostly we will be interested in correlation function between two fields in real time. Yeah. Yeah, in the first contour.
I'm confusing one more thing. So why do you choose this kind of contour? We just choose just first branch and calculate.
Why do I choose this kind of contour? So the most important thing is that I have some place where I can insert the source and then differentiate with respect to that and get the real-time correlation function. All the rest is just part of the formalism. At the end, I will get some result that I will show you how it is related to the physically interesting correlation function. Yeah. But right now, it is just a formalism. Yeah, I have to make sure that the overall evolution is from some time to this time minus beta. Yeah.
Is the position of that vertical contour matrix is like can we shift in the fast?
Is the position of this one? So here I want this to be as far in the past as
Always push it to some minus infinity.
Yeah. I think so. Well, most of the I'm saying that because I don't want to think about this part of the contour. What I'm going to include the source is only in the upper and the lower part of the contour. I actually don't know what other, is there any physical meaning of putting source on this on the vertical part of the contour.
So that vertical contour is okay if it is to the left of all the insertion.
Which, this one?
No,
That one?
that
Yeah.
one you go to.
Yeah. So I'm going to have that all the way to the past. But I think the path integral is always work if the initial and the final point of the contour are shifted by minus I beta, and we impose correct boundary conditions for the field at these 2 points.
Initial start point is like this, and the final point.
Then we are computing something else. The partition function is e to minus beta h, trace of that. So we need the contour to reflect the fact that the evolution has a well-defined Euclidean time. Okay, so it is a slightly unusual path integral because now we have two different sources. We can have a source that lives here. Let me call that J1, and the source that lives here, that is J2, right? And we can differentiate the path integral with respect to the source J. Okay, J here is J1, is both J1, J2, and we will find as we follow the usual derivation, is that up to some factor of plus or minus I that I will not write here, it is the contour, the average of the contour order product of two fields. So if we do that in the usual path integral formalism, the what stay here will be the vacuum average of a time order product of two fields. Since we are doing a path integral with this contour, the field will be ordered as the contour will tell it to order. So let's work out what is this contour ordering. So suppose both x and y are on the upper part of the contour. Okay, then we would have let's see. There are four possible cases. Okay, so let's call that the g x minus y. There is a g11 x minus y, where both x and y are on the upper part of the contour. Then this is simply the usual time order product of phi x and y. Okay, so which means theta x naught minus y naught, phi x, phi y, plus for bosonic field, phi naught minus x naught, phi y, phi x, usual propagator, except that this average is now over a thermal ensemble instead of in the vacuum. Now suppose we are doing something like this, g12 of x minus y, okay, where x is now in the upper part of the contour, so x is now here and y is somewhere here. Okay. So contour ordering means that irrespective of where this x and y are on the contour, this point y is always in the future compared to this point x. Right? This contour goes this way, so y, even if y is here, it will still be in the future with respect to that x. Okay. So that means this g12 is equal phi y, phi x, but y is in the lower part of the contour. Let's recall here that this y have time shifted by minus I sigma. Let's not forget this fact for a moment. And you can easily find that g12 is phi x, phi y average value, and g22 is t bar of x, phi y, where this is the reverse time ordering. Okay. So clearly there we from the path integral, if we differentiate with respect to the source, we can find interesting real-time correlation function. So for example, if one is interested in the Weidmann green functions, just the product of two operators with no time ordering, then we can look at this one, for example. And this one will give us the Weidmann time ordering. The only thing we have to make sure is that we set sigma to 0, so that the time here and time here are both real. Okay, so the Weidmann green function is very natural when we do the contour, where the upper part and the lower part of the contour are shifted by sigma equals 0 on top of each other. So this is one choice that of sigma that people working in non-equilibrium field theory like to make. The choice when sigma is equal 0.
Is the Weidmann the same as what you call the n-in expectation value? I mean, there's this n-in formalism when sometimes
In, yeah, yeah. Yeah, so this is the same state here. It's the same state on both sides. Same state in both sides.
The whole closed time path is the same as the n-in.
The whole, yes, this one, I have to think about it. This one actually tends, yeah, and this one, yeah.
You can get all four of those.
But
Yeah.
still you say n-in in that sense.
Yeah.
Okay.
Yeah, the two formalisms are
But yeah, this one would goes into the usual Feynman propagator at 0 temperature. Yeah, they are equivalent. But
Because in formalism, I thought that, I thought that, the initial and the final time at which you're basically computing whatever correlation function you're taking, those are the same.
the vacuum is the same. Yeah.
So, unlike
There's no reference to what the final state is. It's just the expectation value with the given starting state.
Mm-hmm.
Whereas with Feynman, it's sort of,
Yeah, so
you have to define vacuum at the end.
So yeah, in the end, you end up, some contributions are time order, some are anti-time order. So you end up with, depending on where things are coming from, both.
but my question was, is this equivalent to?
Let me try to say. In the case of thermal equilibrium,
I'm saying that is it true that they're exactly equivalent?
Well, yeah, there's an equivalence between the closed time and the in.
so this distinction here probably is not that important at equilibrium because the initial and final state of the thermal ensemble is the same. If you want to start the evolution from some non-equilibrium state, then this formalism gives you the in correlation function that is more appropriate to do calculations, say in perturbation theory, compared to other formalism. Okay, so let's see what are the properties of these correlation functions. So I will just list them here, and you can easily check them. Yeah.
These correlation functions, will they depend upon sigma?
These are dependent on sigma. In particular, this one is not dependent on sigma because the difference between time here and here, the 1, 1 and 2, 2 is sigma independent. And this one and this one has shift in x minus y by a imaginary time. So if you Fourier transform, for example, you will see that sigma 1, 2 computed at some value of sigma is equal to e to the power of sigma omega times g12 computed at sigma equals 0. And the opposite thing happened at g21. Computed at some value of sigma is shifted by in Fourier component. The Fourier component is shifted by e to minus sigma omega, sigma equals 0. So there is a trivial dependence on on sigma in the correlation functions.
And can we see that beta with infinity limit is at zero temperature?
Beta goes to zero limit is the zero temperature. So the beta goes to zero beta goes to infinity limit is the zero temperature. Beta, yeah. So this part goes to infinity.
So the only part that should survive is the first part, right?
You can think about this way. You can think about this that you can actually shift this sigma to be very large. So all this evolution here in the initial and final sigma project the system into the ground state.
So if sigma equal beta, they have to just have different sign, signal like G1 and G21.
If sigma is equal
It's beta.
beta,
Yeah.
if sigma is equal beta, then what is your question?
I mean,
Is sigma 1, 2 and 2, 1 the same?
just off the side.
Actually, that happened. You can check that by writing down the how they look like in operator language. When sigma is equal beta over 2, this thing happened. G sigma 1 2 is equal G2 1. Sigma. Actually, it's easy to explain. It's basically everything becomes trace of beta h over 2. Phi 1 e beta h over 2 phi 2, okay, and you can use the cyclic property of the trace to show that this G12 and G21 are equal each other if sigma is equal beta over 2. You can think about this way. You have a contour on a cylinder. This contour because you compactified along the Euclidean directions. So if your contour is like this, when the two upper and lower part of the contour are at opposite side of the cylinder, the 2 by 2 matrix of the correlator will be symmetric. The 1 2 and 2 1 grid function are the same.
Is it the same in sigma equal to G or sigma equal to
Sigma equal.
I'm just
Sigma equal.
G1 equal to G1.
Sigma equal beta, and so using this this formula, you can easily relate sigma G12 and G21 at different value of sigma.
So you're saying that G21 is kind of a Wigman function, but G12 is not exactly a Wigman function.
It's just an opposite ordering.
Yeah, but then it's also the kind of Wigman function. Wigman function doesn't know about the time.
The Weigmann function does not know about time
So
ordering.
basically the same.
Let me see. When sigma, let's say when sigma is equal 0, you have. I'm sorry.
Then they become equal time, right?
Then it will become not equal time.
Exactly.
It become.
Real time equals.
It becomes both of these G12 and G21 will be phi. So let's say G12 will be phi 2 at time 0 and phi 1 at time t and x, and G21 will be the average of phi 1 at tx, phi 2 at 0. So there is a time difference between them. And these two operators normally are not equal to each other because the two operator phi, well, let's see, phi, do not commute at a different point in space. On the other hand, you can write down the spectral representation and say and see that both of the function refer to the same spectral density, and so there is a connection between them. Just the spectral density of the two differ by just e to minus some beta omega, some trivial exponential factor.
So the field coupled to J1 and J2 may need not be the same. They can be different, right? So this means there should be some lower indices in your definition of the correlator.
Yeah, so for this, it will introduce some complication in this picture. I'd rather stay with the same operator and compute two-point function. It will be sufficient for our purposes for these lectures, but in many cases, you compute the real-time function of two different operators, and you have to be careful about this relationship between 1, 2, and 2, 1. Any more questions? So, so from this, you can relate, for example, as we see, knowing that the off-diagonal Green's functions are equal when for this particular choice of sigma equal beta over 2, you can, for example, relate when sigma is equal 0, G12 is equal to G21 up to a factor e to minus or plus beta omega. That one can rather easily figure out. At sigma equals 0, there is another nice thing that happens for this particular choice. That is, you can show, and I will just leave it as a homework problem. That's this relationship is hold, and it's rather easy to just look at the time ordering in here, and then sum them up, and see that this relationship holds. Okay, so far all we are talking about is formalism, and now we are going to try to find what we can do with this formalism. So in many cases, the problem, the quantities, the physical quantity that we want to compute can be extracted from linear response. So I'm going to talk about linear response theory. In linear response theory, the question that we usually ask is the following. Suppose I start my system in the thermal equilibrium at t equal infinity minus infinity. Then I turn on some source. Say J, T of x. And typically I want my source for the problem to be well defined. Let me turn on a source and then turn off it at some time. So the source will be localized, and for simplicity, let us assume it's localized both in space and time, and then measure some expectation value of some operator, phi. Okay. So for scalar fugue theory, if we don't have a source, if the theory is E2 symmetric, we will have phi, expectation of phi is equal 0, but we turn on a source, so we can ask the question of what is the expectation value of that phi. So here's the, we have to think about what it is, what does it mean in the closed time path formalism. So for this particular problem, the simplest choice is sigma equals 0, because here now the evolution, this time evolution cancel each other, right? Sigma equal 0. Turning on a source, meaning to us in a system, means that we change the Hamiltonian, but we change the Hamiltonian in an equal way in the upper and lower contour. So J1 and J2 are going to be equal to each other. Physically, the only thing we can do is to turn on the source. That would be that will change the Hamiltonian in a particular way, and that will we will have the same Hamiltonian here, the same Hamiltonian here, and the initial state is still governed by the thermal ensemble at minus infinity. That's guaranteed by this part of the contour. Okay, so now we know that this phi of x is equal to the integral over Green's function, x minus y, multiplied to the source j of y, where the integral is over the contour. Okay. And we can break it into the sum of two pieces. So if I measure the expectation, if I measure the expectation value of phi, I can set this x to be in, say, in the upper part of the contour, and then I have to integrate over y. Yeah. Hello? Hello? Now it's working. Can put it a little bit higher. Okay, so it's a retarded. The retarded Green function is G11 minus G12. So if we turn on source, then we find that the response of the theory to the source is characterized by a particular linear combination of the two closed time path propagators, namely G11 minus G12, that we will call retarded Green functions. And using the properties of the Green function that I have in this board, that can be also equated to G21 minus G22. It's better B because I can put this x in either the upper part and the lower part of the contour, and the result should be the same. So basically, this is another derivation of that relationship. Okay, so now let me, to conclude that, let me show you how this linear response theory is consistent with causality. Basically, we know that this is the time ordered, and this is some kind of Weidmann. And using this operator representation, we see that the retarded Green function is nothing but the average value of the commutator between x and y multiplied by the theta function of x0 minus y0. You can easily check that. And that means that this retarded Green function is non-zero only in the forward light cone, when x minus y lies in the forward light cone. An event turning on a source influences only the expectation value in the future. It will not influence anything that we have in the past. So things are consistent. Okay, a little bit behind schedule. So let me start. So this is a very short course on thermal field theory. I'm going to jump to the topics of hydrodynamics, and I will be talking first generally about the philosophy of hydrodynamics, and then probably in the next lecture we will go into technical details. Okay. So I found out that there are different people understand the word hydrodynamics differently. So when talking to my condensed matter colleagues, everything that is low energy effective theory is they call that hydrodynamics. So the that's the definition that is going to be too broad for me. What I'm going to use is that hydrodynamics is the low energy, any low energy, long distance, long time effective field theory. Let me put that here in quote. That describing a system with a non-zero temperature. And to be more precise, describing an interacting non-zero temperature theory. What happened at non-zero temperature, as I was alluding to at some point, is that we can imagine the system as consisting of many particles. So in a weakly coupled theory, it is actually a good way to visualize the system. If you follow one particle, it travels, and then at some point it will scatter off another particles, and its trajectory gets randomized. There is a typical length scale called the mean free path. Let's call that lambda mean free path, and the associated time with that is some mean free time. In the relativistic theory, they are proportional to each other by a factor of the speed of light. The hydrodynamic theory is applicable if we are looking at time scale much bigger than the mean free time, and the length scale much bigger than the mean free path. Okay, so for these time and length scale, things simplifies a lot, because we don't have, well, roughly speaking, we don't have to follow the microscopic of the theory. We can think about the system as some kind of fluid, and then describe the fluid in using a smaller number of degrees of freedom. What are these degrees of freedom? So the hydrodynamics degrees of freedom. Let's talk about that. So suppose we have some modes. So in this regime, only the modes that relax very slowly will survive. There are a lot of modes that would relax very quickly to zero, and this will be non-interesting from the point of view of low energy effective theory. What is interesting, for example, is say if we have some conserved charge, say some d mu j mu is equal to 0, and then we imagine that we have a state where we have a lump of the charge in space. Okay, and the size of the lump is going to be much bigger than the mean free path. So there are a lot of, you can imagine some charge carriers here, and we just using, for example, a source, we prepare the system in this initial condition, and we can ask the question, how quickly the system will relax to thermal equilibrium. This charge will be distributed along all space, so at the end, all this charge is going to disappear, goes to zero. However, that process will take a long time, and this charge, because it's conserved, things cannot relax over a time scale, say, smaller than the length scale divided by c. Just thing cannot move around with the speed bigger than the speed of light. So in the real in many cases, this relaxation is even slower. So any conserved charge will give hydrodynamic degrees of freedom. So, for example, in this case, this is the density, say density of some baryon number density, if baryon number is a conserved quantity of QCD. And certainly in any quantum field theory, we are guaranteed to have the conserved energy density and conserved momentum. And this will be the degrees of freedom that will be in any hydrodynamic theory. And on top of that, there might be density of some of other conserved charges. Okay. Another class of hydrodynamic degrees of freedom that might appear in the system are the Goldstone boson. So let's consider quantum field theory at zero temperature with a broken symmetry. We know that there are massless degrees of freedom coming from the breaking of symmetry through the Goldstone theorem. If the temperature is such that the symmetry is still broken, then this Goldstone boson have to be taken into account. So in this case, when we have some broken continuous global symmetry, most famous example is helium superfluid. When people first saw how its behavior is so different from the usual fluid, it was a puzzle. But now we understand that the hydrodynamic theory that describes superfluid is different from the hydrodynamics of normal fluid because of the inclusion of a Goldstone boson coming from the breaking of the symmetry. In the case of helium, this is the U1 particle number symmetry. And the last thing is, if we have massless photons, let's call them. So these have to be, more technically, let's assume we have some U1 gauge symmetry that is unbroken, and we have massless photons. The hydrodynamic theory that corresponds to this case is usually called magnetohydrodynamics. Let's say if we write down the behavior of the magnetic field in the core of the Earth, that is the hydrodynamic theory that we would be using, the theory that includes the gauge field, the U1 gauge field, in this case as electromagnetism. So next time we will continue the discussion of hydrodynamics and connect that with the thermal field theory, how one can think about hydrodynamics as an effective field theory.
So the mass field quantities depends on temperature, because if the temperature is high enough, the Goldstone.
Yeah. So here in helium, for example, it's in a